Does anyone have any questions? Okay, today we'll finally be starting part 2 of the course, which is logic. And for this, we'll be using an excellent set of notes by Prabhakar Rogde, and we'll be using his proof assistants. He actually has agreed to speak tomorrow, so he'll give an introduction to his proof assistants, which should be quite a treat. But ahead of that, I'll quickly describe the setup. Logic with implications, the rules of inference for implications, how you prove logical statements about implications, what they mean, well, 2 notions even of what they mean, and I'll start to discuss bidirectional type checking. But first, I'd like to just discuss this idea of inference rules before we discuss it in logic in the context of expressions as we've seen before. So recall that ANAT, let me switch colors, that ANAT is either Z or S of ANAT. And one thing we discussed was 2 approaches to looking at the structure of some given expression. One was synthetic. So let's divide the screen like this. And the other was analytic. So on the synthetic side, let's look at the statement S of Z is ANAT. How can I know whether this is true?
I guess you can build it.
Right, so how would I go about doing that?
You would start with Z.
So Z is ANAT.
And then S of Z.
Yes, so since this, thus, S of Z is ANAT, and then?
S of Z is ANAT.
Yeah. Now, analysis we used for showing that something is not ANAT, but we can also apply the same process to something that is ANAT. It'll fail to show that it's not ANAT, but it will tell us what the structure of it is. So let's say that we have maybe some NAT, let's say N. And that NAT is S of Z, the same one as before. And then you can start by asking questions. So you can ask let's suppose that it's ANAT. Then what must be true about N? Well, I'll write it like this. N is either
Z or S of net.
it's either Z or S of some knots. I'll write S knots, where that should be replaced with some knots. And then we can see that it's the second option. And then K is S of Z. And then we repeat this again. And we find that it's again of the form S of L, let's say, where L is Z, and then repeat. Z is of the form Z. Well, L is of the form Z. And so when we look at the structure of a knot, for example, we can also draw ASTs for the knot expression. So for that knot, we would draw the following AST, S of Z. Now, the thing about being an English speaker, or most European languages, is that we read from left to right and from top to bottom. I think top to bottom is universal. Left to right is not. But in computer science, we say that we frequently draw our trees with the root of the tree at the top. And that's really because, why is that? Because we read trees from top to bottom. And when I read this tree, I see that whatever this expression is, when it's represented as an AST, it is S of something. And what is it as? What is it S of? Well, it's S of Z. And what is S of Z? Well, it's S of something. It's S of Z specifically. And then Z is just Z. So when I draw an AST, is that a description that shows the tree from a synthetic or an analytic perspective?
Apart from analytic?
Yes. Show an analysis of syntax. YS of syntax. And then this is why the root is at the top. Now, we can also show a different type of tree, which expresses a synthesis of that expression. So, for example, and just to conform with Prabhakar's notes, there's one thing that I've avoided this entire class, and that's using sets in this part of the course. So instead of writing, but I'm now going to break that. So instead of writing is a not, I will write is an element of L where L is the set of syntactically valid nats. And you should just think of these as what I've just said is just words. This is just notation. Read is an element of L as is a nat. And so if we looked at the synthetic process, what did we have? We started with, and if we start somewhere, that should be at the top of the page, not at the bottom. We started with the fact that Z was a nat, right? And then from this, we concluded that S of Z was a nat. And from this, we concluded that S of Z was a nat. So what I've just drawn here is called a proof tree. Now, unlike ASTs, the root is at the top. And why is this? Why have I drawn the root at the top? What is the most elegant reason to express why?
According to the NAT rules, Z is the only one that we know as definite value at first. It allows us to establish a foundation for NATs.
Right, so you read it from top to bottom because you're representing a what of syntax. I mean, in contrast to ASTs, you're showing a blank of syntax.
It's like
A synthesis of syntax.
Yes. Because they depict syntactic synthesis. Synthesis. And really, this explains why ASTs have the root at the top, because ASTs are considered about how to break down the structure of the expression that you have. And so when you start breaking it down, you ask, what is it at the uppermost level? Is it a successor or is it Z? That's the most important first piece of information that you have to know. Whereas in this synthesis, you're not starting with something unknown. You're starting from the foundation. You're just starting with the known assumptions that, for example, Z is a nat. And then from there, you use that assumption to conclude that S of Z is a nat. And then you use that assumption to conclude that S of Z is a nat. So proof trees are also rooted trees in the same way that ASTs are, but the two differences are that, one, we draw them with the root at the bottom as opposed to at the top. Well, why do we see that the root is at the bottom? I'll explain why the root is at the bottom, actually. Or rather, why is it that the thing at the bottom should be the root? Well, because suppose you have an analysis of syntax like this. how do you make it bigger? If I have that AST, I can make another AST by adding an S at the top, right? So if I'm adding something, I'd add it at the top. Whereas here, you'd add something else at the bottom. You could continue this by drawing another line. And then drawing the next level. So because you extend the tree from the bottom, that's what tells you that the root of the tree is at the bottom. Because just as with ASTs, you wouldn't modify an AST by modifying its leaves. You'd modify it by using its root to be the child of some other node. Okay, and the other difference is that instead of drawing lines connecting them, we draw these horizontal bars. So I'll give another example of proof trees. Let's think about the language of conditional expressions. So in this language, an expression, let me draw it in colors as before. And what are my first two variants?
True or false?
Yep. So, I suppose that I should say one more thing about gnats. So if we look at the grammar of gnats here, what we can do is we can write this in a different way. Instead of writing a grammar, we can write inference rules. We can write the rule that Z is a gnat. And we can write the rule that if N is a gnat, then S of N is a gnat. So these are inference rules for the grammar of gnats. Now, notice there's something that's interesting, a distinction between grammars and systems of inference rules. In a grammar, both occurrences of not were distinct. So in a grammar, the two occurrences of the non-terminal, as I said before, were independent. And this is because not was not a meta variable, it was a non-terminal. Whereas in here, N is a meta variable. And what does that mean? That means that the n at the top has something to do with the n at the bottom. So specifically, if we take n and we substitute in it, not any nat, because that's what we're trying to define, but any s expression, then you get a valid instance of this rule. So for example, if 17, the number 17, which is an s expression, is a nat, which it's not, then s of 17 is a nat. That inference is valid, although the premises is false. But I had to replace n both at the top and the bottom with the same thing. So in general, the systems of inference rules have a degree of complication that grammars do not. Grammars can't capture, for example, n occurring twice at the bottom. Does anyone have any questions about just this notation for inference rules for this? You should just accept it as a notation for the moment. I've just taken this grammar and I've written it in this form instead. Anyone? Okay. So let's say that as a system of inference rules, let's say that is an element of T, the set of expressions, means is an expression. This is just a piece of notation for the moment. Then as a system of inference rules, how could I write it? So what does the first rule of the grammar tell me?
So like n m elements of T.
So true is an expression, right?
Yeah, so that's element of T, and so is false.
I don't hear you.
And so is false.
Yeah. And then what does the third one say?
For an n, m, and o elements of T.
We called them R, S, and T last time.
Oh
Let's
yeah,
say
RS. Yeah. If RST element of T.
let's write the three premises separately.
Okay.
Then what?
Then if RST is an element of T as a whole.
Yeah. Actually, I don't like my choices of colors. Let's be slightly more consistent and make them blue. So here, R, S, and T are metavariables standing for any S expression. Are metavariables. for any S expression. So for example, in order, you can use an instance of this rule as follows. You can say, consider the expression Z. Well, Z is not in C. Okay, then let's consider true. And then the expression if Z false and true. So if Z is an expression, which it's not, and false is an expression, which it is, and true is an expression, which it is, but overall the premises is false because it's not true that all three of those hold, then we can conclude that this is an expression. So this is an instance of the inference rule. Of the third rule. And notice also that the R at the bottom and the R at the top were connected. I chose what S expression I would wanted to place in place of R, and I replaced both R's with the same expression. So this is a consistent substitution.
Question.
Yep.
So, do we always start out with the grammar and then somehow we relate a system of inference rules to the grammar? Or
so what we're about to see is that grammars are good for describing the syntax of certain things, but inference rules are in general more powerful. And that there are things that you can describe by inference rules that you can't describe by grammars.
Okay,
However, every single grammar can be read as a system of inference rules. So that also answers your question. Every single grammar gives a set of inference rules. That is a true statement. Does that answer your question?
Okay, so, but the follow-up would be, are they different things? You don't need both of them. You can just work with a system of inference rules?
Yes, you can.
So how do you know
that
your base cases or the top of your proof tree is just an assumption? You're just assuming
right.
it?
So when you have a fraction, these are called premises. And these are called the conclusions. Now, these rules do not have premises. You can write them, if you wanted to write them as fractions, you're allowed to do this. You could write them as a bar with nothing over top of them. So these have no assumptions. So that's what indicates that you have starting points. So when you have inference rules with no assumptions, you can either write them in this notation is called fraction notation. If you can either write them with not as a fraction, but just in that way, or you can write them in fraction notation, which makes it clear that there are no assumptions or no premises to that rule. So those are your starting points. Is that clear?
Yes, thank you.
So, okay, and what I was saying before is that we see a difference between grammars in that all three occurrences of expression in the grammar, actually all four occurrences, there were 4 times that the non-terminal expr appeared in the grammar. And all 4 of those occurrences had nothing to do with each other. Whereas in inference rules, we had 3 metavariables, r, s, and t, and each one occurred twice. And each occurrence of that metavariable was connected. So when you went from the general inference rule to a concrete instance of the inference rule by substituting some s expression for every single metavariable, that substitution has to be consistent. So every single r is replaced with the same expression, and every single s is replaced with the same expression, as with every t. Any other questions? So inference rules are just let you conclude something from something. They're actually an inductive way to build up trees. Give an inductive construction of proof trees. So for example, I can consider the following thing. I'll write everything in blue except for the lines. So let me write T and F for brevity. So I know, for example, that true is an expression, false is an expression, true is an expression, right? And then I can say that these 3 things have no premises. So I've constructed 3 separate proof trees. The inference rules let me say that this is a proof tree, this is a proof tree, and this is a proof tree. Then from those 3 different proof trees, I can construct the following proof tree. Right? Now I can construct 2 other proof trees. I can also consider the proof tree true is in T and false is in T. So here are 2 more proof trees. So now I have 3 proof trees in play. Well, I can take all of those proof trees and I can combine them to construct the following proof tree. And in general, we say that such proof trees, so this isn't something that you have to know, this is just a name. These are proofs of well-formedness. Which is the same thing as a process of synthesis. Does that make sense? So in other words, what the inference rules say is that they actually give an inductive way to build up proof trees. What the inference rules say is that if you have any proof tree whose conclusion, that is the thing at the bottom, is R is in T, and any proof tree whose conclusion at the bottom is S is in T, and any third tree whose conclusion at the bottom is T is in T, then you can take those three proof trees and you can combine them together to make this one bigger proof tree where the conclusion at the root is if R, S, and T is in T. So instead of, you can actually take the entire synthesis process and put it into a single proof tree, and you can think of the inference rules as being inductive rules for constructing proof trees. So in this way, the set of inference rules determine all possible valid proof trees, and then you can get all possible expressions by looking at the conclusions of the proof trees. And I should say inductively define all possible proof trees and the conclusions of these trees define all possible expressions. Now here is where inference rules become more powerful than grammars. So here are inference rules for computation. So here all metavariables stand for expressions. As opposed to S expressions. Can anyone tell me what the three inference rules are written in fraction notation? This is for computation. So remember, we had three rules for computation. One began like this. Then what?
ST reduces in one step to true.
Yep. Well, not to true, to what?
To S.
Yep. And so we can take this and we can draw this as a rule. And this rule, we give a name. We call this rule if true. Then similarly, we have another rule, and this is the if false rule. And can someone else tell me what the if false rule is?
If false, ST reduces to T.
Yep. Now, would someone like to treat the more complicated final rule that we had? We finally had a third rule as well. What was the third rule?
On top, you have R reduces to R prime.
Yep. And at the bottom?
You have if RST reduces to if R prime ST.
Good. And what was this rule called? What was its name? So it started with if dash what?
If cons.
Cong.
Okay.
Congruence. So this is a congruence rule. Now, a grammar can't capture something like this. Like if you look at the conclusion here, then S appears twice in the conclusion. Whereas in a grammar, you could just put maybe expression there and expression there, but they wouldn't have anything to do with each other. But here you have S occurring twice in the conclusion. So that's a more elaborate thing. So this is already defines something more powerful than a grammar. Well, I'm not 100% certain that you can't do it with a much more clever grammar involving much more non-terminals, many more non-terminals. Actually, I'm not 100% certain on that. But you can't naively write this as a grammar. Be written as a grammar. And then if you actually look at what you get from these rules, so here's an example. So let's start at the bottom of the tree. Let's say we consider the expression if, and then, oh, I see. Okay, I really need to squish this in. If, and then like these don't really matter. So if we're actually working backwards, actually, okay, what rule were you going to apply here? So remember before when we were, for example, talking about plus and we did justifications, what justification are you going to use at the topmost level? Which one of these three rules applies?
If Kong,
Yes. So the rule that you want to use is if Kong. Let's not determine what the conclusion is yet. Let's, for the moment, just consider the thing inside of it. So the thing inside of it is, in the first position, the R is if true, false, oops, true, false. And that reduces to something. And what rule was used to justify that reduction?
if Kong
rule?
again,
Yep. And then you consider this expression on the inside, the R, the if true, false, true. And now what does that reduce to?
false,
And by what rule did you conclude that?
if true,
Yep. So what does the expression on the second line reduce to? What do I put here?
if false, true, false,
And so what does this one reduce to? Anyone else?
should we reduce that again or keep it as the if statement?
Well, look
Excellent.
at what the rules say. So the rule that you're applying is if Kong. What is the premises of the rule? So this is the premises. And this is the conclusion. So you've justified at the start that if true, false, true reduces in one step to false by the if true rule. So therefore, by the if Kong rule, since you can conclude the previous statements, if true, false, true, true, false reduces to if false, true, false. Now that's the R and that's the R prime. So if you look at the conclusion of the rule, and you look, it says if R, S, T. What are S and T in this case?
For which line?
For the very bottom line.
False and true?
Yeah. And so if you just apply the rule, it's a rule. You follow the rules. So if you follow the rules, what do you get?
If false, true, false, true, false, false, true, or no, we got rid of that.
No, we got rid of that. So, but then I write, what do I write now?
False, true?
Yep. So now you see why on PF1, I had you justify repeated occurrences of if Kong. So on the proofs, you would have written if Kong, if true. As this justification. Now you see why. Well, you had a reason to see why, but now you see why more clearly. So in other words, the inference rules, these three inference rules for computation, they provide rules for inductively constructing a set of proof trees. And the conclusions at the roots of the proof trees say that some expression reduces to some other expression in one step. Now, all of the reductions that the rules let you conclude have justifications in the sense that you can construct a proof tree that justifies why this reduction happens. And then if you want to express what the structure of this proof tree is, you write the rules that you applied at each step. Does anyone have any questions about that? Okay, so now let's get into the heart of the material. So now we're actually starting with logic. So the first thing that we're going to introduce is the language of logic. So this units, there are two units in here. Unit 1, Module 1, is propositional logic. Now, what is propositional logic? So propositional logic is a language for formulas, a language of logical formulas. And this is equipped with some interpretation of these formulas. That gives meaning to the formulas. And what these formulas are is the first ingredient of the formulas is propositional variables. And you might call these logical atoms. So these are just symbols. These are variables like A, B, C, etc. And what they mean is that they represent some fact outside of the language. They represent some assertion. Some assertion. Outside of the universe of propositional logic. Well, potentially outside. Actually, it's fine to say outside of the universe of logic. So for example, you can say e.g. A means it is raining outside. So the statement, it is raining outside, is a logical statement, but we're not going to care about interpreting it as a logical statement, what it would mean for the statement to be true or false, etc. It is a statement that we can think about, and however we think about it, in propositional logic, we can just denote it by a single variable. It doesn't have any structure beyond that as far as propositional logic is concerned. A is just some symbol, a variable name that denotes something that we call a proposition. So that's the first ingredient of these formulas. So that sounds vague, but you'll very quickly get used to it. So all this means right now is that we're going to have a bunch of letters which we're going to consider to be variable names. And then the second ingredient is logical connectives. Oh, well, are the logical connectives. And I can tell you what all of the connectives are. In our language, we are going to have the following connectives. These are implication, and, or, and not. Now I'll write what they mean. So this is implies. This is and. This is or. And this is not. And the way that you remember the difference between and or is and is this. Well, this. And I'm going to explain what the connection is. A capital A in the English language is written as a wedge with this line between it. And the symbol for and is just the wedge. And then the other one is or. So if ever I need to remind myself which one is which, that's the convention that I use. And these can be used for building up formulas. So specifically, I can tell you what the grammar of logical formulas is. So I am going to follow Prabhakar's convention. The convention is that syntactic categories are going to be denoted by common metavariables. What do I mean by this? I'll explain in a second. So for example, if I could write the grammar for nats as follows. Basically, instead of writing nat, I'll write n. So all I mean is that I'm going to use a briefer notation for, instead of nats, I'll just denote them by what looks like a metavariable, but in the grammar, it appears as a non-terminal. And again, the two ends have no connection with each other, which is a bit confusing, but we're going to stick with this notation because the notes that you're using use it. And it's also reasonable. And there's another good reason for not using nats here, which we'll get to later. And that reason is the distinction between nat values and expressions of type nats, but don't worry about that for the moment. Okay, so in other words, I'm just going to give you a grammar now. The grammar for logical formulas, where the metavariable that I'll be using is, so here is the grammar for logical formulas. And these are going to be denoted by the symbol T. So a logical formula is either how many variants do I want? I want 4 more lines. So first off, it can be a propositional variable. Next off, it could be an and statement. It can also be an or statement. It can also be an implication. Or it can be not. And then I switch over to here and I write the T's. And here, X is a non-terminal for propositional variables. For propositional variables. Which will conventionally be denoted by capital English letters. Capital English letters. Well, capital Roman letters. I shouldn't write English. So I'll give you an example of some expressions in this grammar. So I could have a formula such as not B implies A and C. Oh, I've written the not simple incorrectly. This is always a bit confusing. This way, apparently. So here's an example. And then I could represent this as an AST as well. As an AST, what would it look like? Can anyone tell me? What's the root node label?
Are we doing the system of proof rules here or something else?
Sorry, let me correct a thing. Okay, here, the AST label, these are infix. These are not S expressions. So everything I said before about the correspondence between S expressions and ASTs is sort of wrong. But let's imagine that the root of the AST is the symbol. So or not implies and. So if they're sort of infix S expressions, then how would I write the tree, the syntax tree for this? So the root would be an implication, and then what would the two children be?
Left child is not B.
Yes, and not is a root, and then you have B. And what's the right child?
And as a root. And
Yep.
then left A, right C.
Yep. So it's different from what we had before because they're not S expressions. So that might be a source of confusion. But the way that they're built up, an analysis of the syntax of an S expression would be drawn like this. So I'll write warning. Just because the node labels are infix for the things that have two arguments in their constructor. So then the bracketing tells you the structure of the tree. At the top level, this is an implication. That's the variant of the grammar that you use to introduce it. And an implication, that variant has two T's appearing in it. What is the first T? Well, that T is the AST corresponding to not B. And what's the second one? Well, it's the AST corresponding to and A and C. A and C. So this is called the parse tree, maybe. It's really this is an AST. It's much clearer to write logical formulas in infix notation just by really strong force of convention, and also because we're going to introduce some conventions for removing parentheses. And maybe you can call it the parse tree of that expression. But anyway, so logical formulas are defined by a grammar. One of the variants of the grammar has any one of these propositional variables, A, B, C, D, etc. And then the other four variants of the grammar let you construct and statements or statements, implications, and nots of some statements. So that is the language. That is the syntax. This is the syntax of propositional logic. Well, for logical formulas. And we're not going to introduce any new connectives in the next 2 weeks. In the next a week and a bit. These are all the connectives we'll see for the next week. And then later, predicate logic will introduce quantifiers. Later, next unit, next module, will be predicate logic. So we'll have for all and there exists. But that's for later. That's in the last week. So I've now covered the syntax of logical formulas. Now is a good time for a break. Does anyone have any questions before that?
Can I ask a question about the homework?
Yeah.
Will you update the notes or give us like the recording of the lectures before?
Okay, I need to send you Monday's lecture. That's a good point. I've posted 2 homework assignments, and I need to update the lecture for the lecture notes for both of them.
Okay.
So there are 2 homeworks on the homework page. And one of these is a programming problem on higher order logic. Oh, sorry, on higher order functions. So one of them is a function using fold-R and map. Using fold-R and map. Filter map. And the other is a proof about lists. So for this one, I will provide a sample proof about lists and proof rules for lists, which the notes currently don't have. I need to update the notes. And I'll do this ASAP. I already have most of that written. Then for this one, we'll use my Monday lecture video. And I'll send you a link. Although someone's told me that you actually don't need a password to access them from Blackboard. But I'll send you a link anyway, and I'll post it to YouTube eventually. Now, both of these are relevant for the midterm. Must do both before midterm. Ahead of the midterm. Now, the proof is similar to the previous 2 proofs. About gnats. And this problem, the filter problem, well, it asks you to implement unique left and unique right using those higher order functions without using recursion on your own. So really, it's just a question where you have to take those solutions and you have to adapt them using higher order functions. So in some sense, both of these problems are more of the same. You don't have to learn something fundamentally new, like you did on the homework over the past 2 weekends. But I'll also have another homework assignment due Sunday about proving logical formulas. And that's the new content on the midterm. And this will be the 4th proof assignment, PF4, on using Proust. And this is what we'll discuss today and tomorrow. So this assignment, it's not hard. You don't have to come up with something incredibly clever to do it. Rather, you have to just read through this material and ensure you understand it. So it's a straightforward problem if you go through the material. You don't have to, like, so this is relative to doing PF1 and PG2. When those problems were very hard for you to do because you needed to figure out how even categorically it's possible to solve a problem like that. So those were hard and substantial things. This one will not be as hard and substantial. It'll just be reading through Prabhakar's notes and actually listening to what he says tomorrow and listening to what I say about logic. So there will be a bit of this logic content on the course, but all of that content will be covered by the end of Thursday's lecture. Nothing that I discuss on Monday will actually be on the midterm. But I will update the notes, actually. I'll update the notes to have everything that would be relevant for the midterm for proving things in my way, and then I'll link to the relevant sections in Prabhakar's notes for the logic. Does that answer your question fully?
Yeah.
Okay, so let's take a break until 3. And I'll leave. Okay, well, I wrote resume at 3. I'll leave the grammar for logical formulas here so you can look at it while we're away. This is the only thing that matters now at the moment. That. Okay, and we're back. Any questions? By the way, I'll give an outline of how many questions there are on the midterm and what the topics of those questions will be. Well, to some degree of, I'll decide, I will decide by tomorrow how much I'm going to reveal, and I'll give that outline at the end of tomorrow's class. But really, the logic is going to be one question, the material that we're currently covering. But everything else will really be the proofs that you were doing before and the racket programs that you were doing before. And all of the racket programs have to be structurally recursive. So midterm outline at the end of tomorrow's class. But I think I can tell you the hours that the midterm will happen between. So I'm 85% sure. Maybe that's an exact exaggeration. Let's say 80% sure that I want to run the midterm from 8 p.m. on Monday and this is NYC time, until noon, or let's say 11:59 a.m. on Wednesday. So that's about 40 hours. And apart from the logic material, it's more of the same. Writing proofs in the formats that I strictly specified and writing racket programs using pure structural recursion and only a very small list of built-in functions. Any questions? What do people think about the time of the midterm?
Sounds great.
Cool. Good. Okay, now, so let's discuss the meaning of logical formulas. And the first thing about this is typically in a Math 250 class, this is what's done on the first or second class. In previous Math 250 offerings, this is what they do on the second class. Let's say L2, lecture 2. And this is truth. And this is a very particular notion of truth called the Boolean interpretation. So since Math 250 does this in the second class, they consider this very important, but it's actually going to be irrelevant for our class. But irrelevant for us. And I'll explain why. So the question that we're trying to answer, well, I mean, the question that we're trying to answer even before we get into the irrelevance interpretation is, what is the meaning of a logical formula? Let me shift this here. And the conventional mainstream answer is that it's the meaning of a formula is a truth value, whether the formula is true or false. So there is some notion of truth, and no matter what logical formula you write down, you can classify that formula as either true or false. So every formula may be classified as true or false, is classified. As either true or false. Now, how do we get a notion of truth out here? And this happens by, so we start off with the idea that a propositional variable is either true or false. And I'll write capital letters, true or false. But we don't know this. So for example, if A means it is raining outside, then this is either the case or not. And you can check which one it is by looking outside of the window, maybe, but that's outside of the scope of propositional logic. For propositional logic, all it treats it as is a variable. It doesn't look at the internal logical structure of the sentence. And propositional logic knows that, okay, the things that I care about, A is some locus to which truth applies. You can meaningfully say whether A is true or false, but you can meaningfully say that it's one or the other. And this introduces the notion of a valuation. A valuation is an assignment of true or false to every propositional variable. What does it mean to every propositional variable? You can say in play, so that we're discussing. So for example, let's say we have that logical formula before, not B implies A and C. Then there are three propositional variables in play. What are they?
BAC.
Yes. And then evaluation is an assignment to each variable of one of true or false. For example, so I'm going to denote this by this script v, defined by, so the valuation of, so I'm going to say the valuation of A, let's say, is true. The valuation of B is something, and the valuation of C is something else. So I've just made arbitrary choices, but I've made some choices. So the valuation consists of these choices. We've chosen so true or false are called truth values. In programming, truth values are known as Booleans, but in logic, they're known as truth values. And so evaluation defines a value to each propositional variable, and that value is a truth value. Then, after you make these choices, the valuation extends to all logical formulas. Using these variables. And the way that you do that is by giving a truth table for each connective. So let's say that I have meta variables for formulas. And let's say the formulas are going to be, let's say, T and S. And then here I have the statement, for example, T implies S. Then if T and S are logical formulas, those logical formulas are either true or false. And if we look at all possible choices, all possible things that could happen, this could either be true, 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 false. Then what are the other two possibilities?
False, true, and false, false.
Yep. And so based on the truth value of the logical formulas T and S, we give a truth value for the logical formula formed via their implication. So true implies true is true. True implies false is really bad. True should not imply false. So for example, if by taking a true premises, you conclude something false, then that breaks the entirety of logic. So true implies false is very bad. This is false. False implies true is sure. If I'm the president of the United States, then I can abuse my privileges to get lots of money. That is a true implication. Actually, if I'm the president of the United States, then I'm also the Pope. The first case was an example of true false implies true. This is the second is an example of false implies false. So false implies true is if I'm the president of the United States, I can use my abuse my power. And the second is if I'm the president of the United States, then I'm also the Pope. Oh, actually, no. No. What I said is wrong because I can't abuse my powers of president. So that's a false statement. So both of those would be instances of false, false. Anyway, so this is how, for example, a logical formula built using an implication. Because if we look at the grammar again, the grammar, a logical formula is either a propositional variable, and the valuation defines what the true value of any propositional variable is, right? Then let's say the formula is built with an implication. Well, I tell you what the true value of that is based on the true value of the factors. And that gives a recursive definition for what the true value of any logical formula is after you give such tables for every single connective. So for the other connectives, if you have T and S, and then you consider T and S, and then if you take T, S, and then consider T or S, and then if you just have T and you consider not T. So this is what mainstream propositional logic says the meaning of a logical formula is. But as we'll see, the notion of truth is really overhyped. Truth is less meaningful than you think. Oops. So let's finish these tables. Let's do the one for not first. If T is true, what should not T be?
False.
And the other one, not of false, is
True.
not true is false, not false is true. Okay, what about and? True and true.
True.
True and false.
False.
Yep, they're not both true. Then false and true is the same thing, and then false and false.
True.
No.
I mean, false.
If
sorry.
you say, right. So if I say, for example, I am the president of the United States and I am the Pope, is that statement true?
False.
Yeah. Two false statements don't make a true statement in an and statement. Okay, what about ors? True and true. True or true?
True.
True or false?
True.
Yep. Similarly here, and then false or false?
False.
Right. So we have here given 4 truth tables. And those 4 truth tables corresponds to the 4 variants. So there are 5 variants in the grammar of logical formula. They are propositional variables, which is the thing that we assume a truth value for. We make arbitrary choices for those. And then we have 4 logical connectives, which can be used to build logical formulas. Implication, and, or, and not. And now, using all of these rules, this defines a valuation on every single formula. So this extends the definition of V to every logical formula. So as an example, if we considered the valuation of not B implies A or C, A and C, then the recursive definition says that this is the valuation of not B which is a true value, implies the valuation of A and C. So now we consider the logical implications as operators on truth values. True implies true is true, for example, right? And then we apply the recursive definition again. And this is the same as not the valuation of B implies the valuation of A and the valuation of C. And then we go and we look up what all of the definitions are. So we arbitrarily made choices, right? Above. A, B, and C were true, false, and false. So valuation of A was true, and then we had false and false. And so we have not false implies true and false. And then these, what is not false? Not false becomes what?
True.
Okay, and here true and false becomes? What is true and false? The true value of true and false.
False.
Yes. So this statement reduces to true implies false. And what's the value of that?
False.
Yep. So the valuation gives this formula, the valuation gives this formula false. But that depends on the choices. The valuation depended on the choices. So here is the Boolean interpretation of a logical formula. Of propositional logic. So this is what they teach in the second lecture of regular Math 250. A logical formula is true if and only if it is true under any evaluation. Every valuation. Now, if there are, notice that if there are n different propositional variables, then there are 2 to the n evaluations. As each can be true and false. Each variable can be true or false. So if you have a formula and it has n propositional variables, then you have exponentially many different valuations. And if no matter which one of these exponentially many valuations you take, you extend the valuation to the logical formula, and no matter what it gives true, then we say that the logical formula is true. So to give an example, consider, here's a simple case. Consider the formula A implies not A. How many propositional variables are there in this formula?
1.
Right. So there are, or how many valuations are there?
2.
Yep. And what are the 2 valuations?
A and not A.
No, the valuations are defined by choosing A to be.
A could
So-
either be true or false.
Yes. Let me scroll down a bit. So A is either true or false. And each one of those defines a different valuation. Now, if we choose this valuation, then A is either true or false. So now let's consider what not A would be, and let's also consider what not A would be. And then let's consider what A implies not A would be. Okay, so what is not A in either of these valuations? What is it in the first one?
False.
And in the second one?
True.
Okay, what about not A in the first valuation?
True.
And
False.
okay, consider the statement false implies true. Is that true?
Yes.
Oh, sorry. No. We're not considering the statement false implies true. We are considering the statement true implies true, right? A implies not A. So true implies true is
True.
and then here we're considering false implies false, right? What's the value of that?
True.
Yep. So we see since for every valuation gives true, hence A implies not A is true. If but a single valuation gave false, we would say that it's false as a formula. And by the way, writing tables like this is due to Wittgenstein. Which is surprisingly recent. And this is in the Tractatus, 1917. Tractatus Logicus Philosophicus.
I just know his books are, even though he's like the philosopher of language, his books are unable to be read properly because they're just so poorly written.
Well, the one thing that I learned about Wittgenstein is that he writes everything briefly. His sentences are short. The entire Tractatus is 70 pages.
Yeah, it's
And then-
very scatterbrained is how I learned it. And so he doesn't flow any thoughts together. He just randomly spurts ideas on the page. And then his second book just destroyed everything he wrote in his first book.
That is true. He went largely against what he did. In his first book, he was trying to construct a perfect language. He said language should be like this. And his second is like, well, okay, that's not what language is in practice. Let's consider this. And in his second book, actually both books, they explore a lot. So especially philosophical investigations, the tone of the book is that he goes through the process of thinking things through. So he says, is something like this? Well, okay, this is what we do if we think this. So instead of saying some definite position, he tries to make the book read as the process of thinking through the questions instead of giving definite answers. And so that leads some people to maybe say it's scattered-brained, but it's not excessively verbose and wordy. It's very succinct. Wittgenstein writes very short sentences. So that is one thing that I like about him. But it's also very dense because in the Tractatus, it's 70 pages, and then Philosophical Investigations was published posthumously, and he didn't publish any major books for the remainder of his life. So he got world famous from a 70-page book, which then he didn't publish anything else for the remainder of his life. But it is a particularly interesting 70 pages, which, among other things, introduced logical tables. Okay, but I'm sorry, Wittgenstein, but this is not what we're going to do in this class. Truth is overplayed. So yes, unfortunately, that innovation is not what we're using. Does everyone understand what this idea is? So this is what the department would have me teaching in conventional math 250. There are logical There are propositional variables, there are logical connectives. Propositional variables are either true or false. The connectives are either true or false depending on what the values of the things that they're connecting are. Then evaluation is a choice of an assignment of a true value to every propositional variable. And then you take all of these propositional variables, and the valuation extends from propositional variables to all logical formulas using the truth tables. Why does that definition work? Because this definition is inductive. Well, it's recursive. It's a recursive definition. And why do recursive definitions work? Because logical formulas are defined inductively. You give recursive constructions over inductive definitions. In homework, in the first homework, so where you did proofs, you proved things about inductive constructions. In the latter homeworks where you wrote programs about lists, you wrote recursive functions on things that were defined inductively. So you're familiar with this already from before. And then the meaning of true or false for a propositional formula is whether every single possible valuation gives a true or false. And if there are, for example, so the powers of 2 are 1, 2, 4, 8, 16, 2, 4, 8, 16, 32, 64, 128. So if there are 7 propositional variables, you have to write down 128 different possible options for every single combination of true or false for the 7 variables. And then you have to do the valuation for every single one to determine whether it's true or not. And then if there are 10 propositional variables, then you have to consider 1,024 different possible valuations.
Question. So
Yep.
is this, is this practical then, or how do you get a handle on this if it's exponential?
So that's a definition of truth. And this is where proof comes in. Proof can tell you that something is true without checking all possible valuations. Proof lets you, so let's imagine that we only had a notion of truth. This was the only notion that we had. Then suppose you wanted to convince someone that a logical formula was true. Then you'd have absolutely no option but to go through all of the exponentially many options. There'd be nothing else that you can do if the only thing that you have is truth. But there are ways to go about that. There are ways to convince someone of the truth of a proposition without going through exponentially many formulas. And you can do that by giving them a proof of the logical formula. These allow concise expressions or concise constructions that immediately tell you what that can convince you that that prove the truth of a formula. And then, so truth and proof are 2 different notions. Well, instead of saying proof, I'll say provability. Are different notions. Now, regular Math 250 often confuses them. Blends and confuses them. For us, they are separate. In fact, we won't discuss truth. In fact, we won't consider truth. So the really important lesson, so this was a long digression on the Boolean valuation. We won't use the Boolean valuation in this class. We'll work with provability, and I haven't told you what proof is yet. So I'm going to introduce a system of proof. Well, what is proof really? Proof is some system for establishing the validity of propositions. A proof system consists of rules of reasoning. And we'll show you one. Now, you'll be actually really surprised to know that there are also different truth systems. Well, I'll say different notions of truth. The Boolean interpretation is not absolute. So for example, in this class, actually, we will not be able to prove, we'll think we will, our proof system will be constructive. So for example, the formula A or not A will have no proof. Now, there is a notion of truth that makes this formula false using, for example, Kripke semantics. Oh, I'm going to totally misspell Kripke. That's bad. He's at the CUNY Graduate Center, by the way. Now, well, Princeton mandatorily retires people at a certain age, just like Cambridge. I don't think Princeton any longer mandatorily retires people, but some time ago they did. So for example, our department has Milner, Fields medalist. In fact, one of only 4 mathematicians to have won all 3 major prizes in mathematics: the Fields Medal, the Wolf Prize, and the Abel Prize. And the reason that we have Milner is because he was mandatorily retired from Princeton when he reached a certain age. And so Kripke similarly was mandatorily retired from Princeton, and the CUNY Graduate Center got him. Using Kripke semantics, one can define a notion of proof. A notion of truth. In which this formula is false. Now, just to give an example, in the Boolean interpretation, let's do the truth table. So how many propositional variables appear in here? How many propositional variables are there in this formula?
Just one.
Yep. And what are its possible truth values?
There are two types of evaluations. Because
Yes.
the one is 2.
Okay, so if A is true or false, then what is not A in either case?
False and true, respectively.
And what is true or false or true? Well, what is true or false?
True.
And similarly, false or true. So in the Boolean valuation, this is true. The Boolean notion of truth says this is true. But but we won't be able to prove it. And in fact, there are notions of proof in which that formula is false. So Kripke semantics provide a notion of proof such that everything that is provable, such that proof coincides with truth in our system of proof, which will be constructive. So this is a notion of truth for constructive logic. For constructive logic. And I don't know whether I'll have enough time to do this in the class. Maybe I'll do it in the very last lecture. But either way, we're downplaying truth. We're going to talk about proof. And I'm now going to introduce our proof system. So how can I convince you of the validity of a formula without checking every single possible valuation? And the proof system that we'll use is called natural deduction. And this is a proof system. So what we'll do is we'll start off with a very restricted form of logic. And we'll call this the implication fragment. Let's see how I'm doing for time. Okay. Yeah, I want Prabhakar to speak at the start of next class, so I want to get through everything that I need to get through today. So the implication fragment is as follows. It's logic, but only with implications. So the language will now be this. This is the grammar. A logical formula is either a propositional variable or an implication. So this is the grammar for logical formulas of implication. Involving implication. Only. And we'll develop a proof system for only this restricted logic. And so in this proof system, I'm now going to define rules of reasoning. Well, actually, before I define rules of reasoning, let's discuss this informally. So what this language has is either propositional variables representing atomic logical statements like it's raining outside or other things. And then you have formulas that involve implications. So an example of a formula that we can write is something like A implies A. Let me just check if I want to do it like this or not. Okay, so what does it mean to prove an implication? What does a proof of an implication look like? Well, think about, go ahead.
Is it like if then, or are you thinking of something else?
Yeah, I'm thinking about, so this logical statement says if A, then A, for example. So if you want to prove if something, then something, how do you prove it?
Well, we've used hypothesis of induction before. Like
You wouldn't use induction, but you use hypothetical reasoning, right?
Okay, yes, that's what I mean, yes.
Okay, and so what is hypothetical reasoning you were about to say?
Suppose A.
So, okay, let's say a proof of A implies B. A implies B is what? Go ahead. You were about to say it?
Suppose A.
I'll say supposing A. Go ahead.
Then
Then what?
B.
Well,
Too soon.
what is a, well, here the question is, what is a proof of this statement, right? So the statements themselves are distinct from the proofs of the statements. How did we do hypothetical reasoning? What was the template for hypothetical reasoning? A proof of A implies B is just a proof of what?
Something that follows from A.
But specifically, what is it that we want to show follows from A?
You want to show that B given A?
So, in other words, a proof of A implies B is a proof of B, but you've supposed A, which may use A as an assumption. So in other words, a proof of A implies B is just a proof of B, but where you have an assumption at your disposal, right?
Question.
Yep.
If you're supposing A, do you suppose A to be, like, do you do separate proofs for each valuation of A?
There is no more valuations. We are not considering valuations anymore. We're now, we've left truth behind. We're now just describing a system of proof that is completely oblivious to the notion of truth.
So we're just supposing A to be like an axiom sort of for our proof, right?
Yes.
Okay.
So basically this is, yes, assuming you think of A as an axiom. You add an axiom that lets you conclude A. But now what we've noticed then is that you've supposed something. Well, what if the statement is, let's say, A implies A? Then a proof of this would be a proof of A implies A. That can suppose A, right? But then what is the proof of A implies A? Well, that's just going to be a proof of A, where you also suppose A. And in general, what about a proof of, here's a diff other statement. A implies A is sort of trivial. Now consider the statement A implies B implies A. So this proof, after you use hypothetical reasoning twice, you will have two assumptions, right? And so actually we need a way to keep track of assumptions. There is a context. I'll write the word in a different color. Of assumptions. And this is typically denoted by gamma. Gamma is a metavariable for a context. So a context is a collection of assumptions. And what we're going to actually write is the following notation. And this is called a sequence. And the notation is gamma. And then you have this symbol, which is called a turnstile. And then you have a logical formula. So here, gamma is a context. I'll write it in blue. Also, am I writing my turnstiles backwards or not? I'm writing my turnstiles the correct way. So gamma is a context, which is a collection of formulas which are assumed true. Assumed true. And then T is a logical formula. It's not a true value. So just to clarify, the letter T for the remainder of this class will mean a logical formula. It's not the true value true. It's any logical formula. And so this notation is read as gamma proves T. So in other words, or from the assumptions in gamma, one can prove T. So these are the types of statements that we'll be making. We'll be saying that some collection of assumptions allow us to construct a proof of something. And now with this, I can give you the 3 rules of reasoning. So here are the rules of natural deduction. And these are going to be inference rules. So the most basic assumption is that if you have some context, and by the way, we'll write gamma comma something to mean that T is in the context gamma. So suppose your assumptions include T, then what can you conclude? If you've assumed T, then what do you know at least, in the least?
T.
Yes. So if you assumed T, you can conclude T. And this rule is called the assumption rule. So informally, this says, so I'll annotate it saying that this means gamma includes the assumption T. Well, no. So this does not mean that. The context gamma comma T is gamma and also T. So this is a notation for adding T to the context. And then what this rule says, if you assumed gamma, if you assume T, you know T. You can prove T. You know T. So that's a fairly non-controversial rule, right? That sounds reasonable. Doesn't that totally sound reasonable? Okay, here's our second rule. Suppose you have some context gamma, and you also have T as an assumption in there. And suppose you're able to prove W. So using the assumption T, let's say you can prove W, where W is some other logical formula. Then what can you prove in the context gamma, removing T from that context?
If you know T, if you assume T, you know W.
So that's what the top line says. But what should the bottom line say? What logical formula do you know? Remember the grammar of logical formulas. In our case, a logical formula is either a propositional variable or an implication of one thing to another thing. So what logical formula can I conclude?
T implies W.
Yep. And this assumption, this rule is called implication introduction. If in context gamma, I can prove gamma with T plus T. I can prove W. Then in context gamma, I can prove T implies W. And this is called implication introduction. So if this rule is called implication introduction and it lets me introduce an implication, how do I use an implication? What rule lets me make use of an implication? So suppose in context gamma, I can prove T implies W. What else do I need to know to use this implication? Here, let's put an example. Suppose that suppose that it's true that if it's raining outside, then I ought to bring an umbrella. What would allow me to conclude that I ought to bring an umbrella? So I want to conclude that I ought to bring an umbrella. And I know that if it's raining outside, then I ought to bring an umbrella. So what else do I need to know to make this conclusion?
T implies T.
Well, T implies T will turn out to be always true, but what do I need to know? So I know that if it's raining outside, I ought to bring an umbrella. And I want to conclude from that I ought to bring an umbrella. So what else do I need? What piece of information will allow me to make that conclusion?
Well, T has to be in the context. Is it in the context?
No, it doesn't. We're not assuming anything about the context here. But we're going to need another assumption. We're going to need another hypothesis. Sorry, we're not going to need another assumption. We're going to need another. So I said, what did I call and we did another premises for this inference rule. But don't think about the rules. Don't think about context. Just think about the statements. If it's raining outside, then I ought to bring an umbrella. What would allow me to conclude that I ought to bring an umbrella?
It's raining.
Yes, exactly. So if I know this statement that if it's raining outside, I ought to bring an umbrella, then I can look outside of the window, determine that it's raining, and then conclude that I ought to bring an umbrella, right? So if in context gamma, you can prove T implies W, and in context gamma, you can prove T, then in context gamma, you should be able to prove W, right? And this statement is called implication elimination. So these are the three rules of reasoning. There are only three. So everything that you can prove using this system of deduction follows from these three rules. That is the complete set of rules of reasoning. So I'll give an example in using these rules. By the way, does anyone have any questions about these rules?
So this is it's an example of a proof system, or?
Yes, this is a proof system. These three rules constitutes their inference rules and will show you how they allow you to prove statements. The third rule is, by the way, called modus ponens. And lets me use an implication. So let's consider, so let's do an example. Let's consider the statement A implies B implies A. Or do I want to do something more complicated? Okay, let's do a easy one first. A implies B implies A. So I want to prove this using no assumptions. So if there are no assumptions, then I write nothing for the collection of assumptions. So I would like to, from no assumptions, to conclude that A implies B implies A. This is the conclusion that I'd like to draw. What would allow me to draw that conclusion? What rule would I use at this step? So here are the three rules. I should write the three rules again. So the three rules are gamma, comma, t allows you to prove t. This is assumption. Then you have if in context gamma with t, you can prove w. Then in context gamma, you can prove t implies w. This is implication introduction. And finally, for implication elimination, if in context gamma, you can prove t implies w. Whoops. And in context gamma, you can prove w. Then context gamma proves w. And this is implication elimination. So what rule would I use to conclude an implication?
Oh, second rule.
Yes, implication introduction.
Yeah.
Now let's look at the form of the rule. This is basically hypothetical reasoning. You're using hypothetical reasoning. How do you prove A implies B implies A? Well, you assume A, and then using that assumption in that context, you try and prove B implies A, right? Now, how do I prove that? How do I prove that implication? What would I use? What rule would I use to conclude that implication?
Third rule.
But my assumptions don't include, third rule. So what would my assumptions have to be then? So if W is B implies A, then what would T be? My assumptions, so how do I prove B implies A in general? Well, what would I use to prove an implication? Think about your first assignments, your first proof assignment. What do I do again? Well, okay, come on. I can show you an example of the third rule next. But in this case, the third rule, let's say we tried to use the third rule. Then I would need that gamma proves, what is T? What should T be if I want to use the third rule? Well, not gamma. The context is A. So I would need something implies B implies A. Notice how the statement is now becoming more complicated. But I don't want the statement to become more complicated. I want the statement to become simpler. So what do I use? What rule do I use? Come on, there are only 3 rules. It's not the third one. Which?
Is the second one?
Yes. And so I assume B as well. Now my context has 2 assumptions. And I consider the proposition just A. Now, A is in my context. And I could also rewrite this as B comma A. The order of the assumptions doesn't matter. So what rule can I use to conclude A?
The first one.
Yes. So this is a proof tree of this formula. So here, the proof tree starts with no assumptions, and then I can use a process of synthesis to conclude the sequence at the bottom. So from no assumptions, I know that using A and B, I can prove A. Now, that implies that from the assumption A, I can prove B implies A. I've moved B out of the context to form an implication. And then I move A out of the context to form an implication. So this is a proof of this proposition that did not use, this is a proof, this proves A implies B implies A. I'll give another example. Any questions about this before I scroll down?
Yes, it's the point where you're removing variables from the context. What's the purpose? I think I'm missing the point on that.
So the implication introduction rule says that if I have an assumption in a context and I can prove something, I can move the assumption out of the context and form an implication. So think about this as just a syntactic rule. Look at this rule syntactically. So if I have some context, and in that context, I have some assumption, and that assumption in that context lets me prove W, then I can remove this from the context. And with that smaller context, I can prove T implies W.
Okay.
By the way, these rules are about to become a lot more clear when I do the next thing. These rules are going to become evident, self-evident, when we introduce proof terms. For the moment, by the way, what we're doing right now is standard Math 250 material. But we're about to do something much better than standard Math 250 material. Okay, but I didn't answer your question exactly. Can you ask something more specific?
Okay, when we went through this example, we kind of went from the outcome to the top, like we did the bottom up approach.
Oh, well,
that have a
when you read the
purpose?
tree, you read it from the top to the bottom, right? But
Yes.
we don't know what the tree looks like from the outcome, so we were trying to discover the tree going backwards. But now that we finished it, that completes the proof. So we were trying to discover a proof. I could have shown you the proof from top to bottom. That shows you the proof. But we were trying to discover what the proof should be. So think back to what we were doing before. Whoops. Let's go way back to the start of the lecture. Here, when I was trying to show you the proof tree for this computation, I started at the bottom and I wanted to know that. And then I said, well, in order to make a step from there, I would have to apply the if congruence rule because the first term was an if statement, not a true or a false. And then I asked what rule would apply to that one. And then so I built it from bottom to top because I was discovering it. But if you read the justification, then you read it from top to bottom. Does that make sense?
Yes. So then if you're trying to prove something, if you don't know what the proof is yet, you would use
Yes.
the bottom-up approach.
Yes. But the proof is still, the proof after it's written shows a synthesis. It shows a synthesis of reasoning that lets you conclude it. But you don't know what the proof is at the start, so you're trying to discover it. So you start at the bottom and try proving it. However, in this class, this isn't how we'll do proofs. Once again, we're going to do something much, much, much better than this. Let's do another example. Let's consider A implies B implies B. So I'd like to prove this from an empty context. What's the rule that I use?
The second rule, IS.
Implication introduction. So I assume A, and I'm trying to prove A implies B implies B. What do I do now?
Same rule.
Yep. So now my context has two assumptions. The first is A, and the second is A implies B. And I'd like to prove B. How can I prove B? What rule would I use?
First rule.
But I haven't assumed B. I can't use the first rule. It's
Third
not
rule?
in my assumptions. The third rule. So in order to use the third rule, what would I need? I need my context, which has A and A implies B. In that context, I would need to be able to prove first A implies B, right? And then in the same context, I'd also need to have a proof of A in order to use it, right? So that's what I need in order to use the third rule. But how can I conclude both of those things? Let me actually, erase this and extend this line like this. What justifies these two steps? Like what justifies this?
First rule.
Yep. I've assumed it. And what about this?
Also first rule.
Yep. So here is a proof tree for the statements. From no assumptions, I can prove that A implies B implies B. Now I'm going to show you a complete alternative to writing proof tree terms. And that really brings up the question of what is a proof. So this is where we depart from Math 250. Here is what we do better. Prepare to suddenly understand proof trees in a much clearer way. What is a proof? Well, okay, what is a proof, really? You wrote proofs on your first assignment. What were they?
One of them was equating the add and plus operation.
No, but what did it mean to prove something? What did you actually produce to prove something?
Well, we started with the definitions of said operations, and then from there, we used the rules established by definitions in order to reach another conclusion.
Right. And so you can also think about that as some process that actually used the rules and used the assumptions to reach some process, right?
Yeah.
So in some sense, a proof involved some doing. And for example, I gave some suggestions that if you looked at proofs like by the anonymous method, then there was an interpretation to those where using the anonymous method, if you wanted to specialize it to anything, you'd substitute, right?
Yeah.
For any specific value, and then you get a proof. And then induction would be some recursive construction using a proof. And then hypothetical reasoning was, well, if you assume A and you prove B, you can get a proof of B by taking every place you use that assumption and replacing it with a proof of A. And those are sort of active things. So there are two perspectives. One is that a proof is a syntactically valid entity, a syntactically valid proof. Proof tree. A proof is just any collection of symbols that satisfies the rules. And the second is it's really a program. Proofs do things. Proving things is a process. And so there's this idea that of thinking of proofs as programs. And this is called the Brouwer-Hoiting. Let me see if I can get Hoiting correct spelling. Oops. And then Kolmogorov. Interpretation. So Brouwer is a famous mathematician who started his career in topology, but then shifted over to intuitionistic logic and really opposed anything formal, which is very in contrary to the spirit of the work that he started with. His student Hoiting formalized Brouwer's intuitions. And in fact, Brouwer's name on the BHK interpretation, this is also called BHK, is more of a formality. And then Kolmogorov, ну, это очень знаменитый русский математик. Родился в каком году? Как в 1907 году делал что? Топологию, логику, динамики, классической механики и много других областей. И знаменитые студенты, как Гелфанд и другие. Well, yeah, what else is there to say? Kolmogorov is cool. Okay, so a proof should be thought of as a program. And then if a proof is a program, so the syntactic entity of a proof should be thought of as a program. And so here is where we introduce this idea of proof terms. And this is where lambda calculus comes in. So remember that lambdas represented functions. So here is the grammar of lambda calculus. We're going to denote this non-terminal by a standard meta variable, a lowercase t. So a term in the language of lambda calculus is either a variable, lowercase x, a lambda term, lambda, or I want to make that green. It's can be a lambda of some variable followed by another term, or it's an application of a term onto a term. So this is a grammar for the terms of lambda calculus. Terms. And so x is a meta variable ranging over variables. Now in rackets, we used a slightly different lambda notation. We had brackets after the variable, and there could be multiple variables. In the language of lambda calculus, this isn't possible. You can only have one. So here are some examples of lambda terms. You can have lambda x, x. And if we think of the lambdas as functions, this is the identity function. Then you can have something like an application. So by the way, these three things, I'll write what their names are. These are variables. These are applications. And these are called abstractions. Or another way to think about it is that these let you form functions, and these let you evaluate functions on arguments. So another thing that you can consider is, for example, taking the identity function and evaluating it on the variable y. Now, at the moment, we are only considering these as syntactic entities. So I haven't defined what evaluation is yet. We won't consider evaluation yet. But if we think of what a proof of an implication is it's a proof of whatever it is that is on the right-hand side of the implication, but somewhere in the proof you might use an assumption, right? And then if you have a proof of that assumption, then you can plug in that proof into every place where you use the assumption, and you can get a proof of everything. So for example, if you have a proof of if it's raining outside, I ought to bring an umbrella, and you have a proof of it's raining outside, then you can combine those things, by substitution, and get a proof of I ought to bring an umbrella. And so proofs are going to be represented by lambda terms. So let me just write down, okay, then the notation changes, sequence changes, to in context gamma, T is a proof of T. So this is read as in gamma proves T with proof T. So our sequence will now encode what the proof is. So this is vague at the moment, but do you have any questions about it?
Just in the grammar for the lambda calculus terms, the dot.
Yes.
What does that? How do you read that, or what is that? What is it?
Okay. So remember in rackets, we had expressions like this, lambda xx, right? Where x is the formal parameter. This is called the formal parameter. Well, in lambda calculus, in the way that it's usually denoted, this is, by the way, from the work of Church. He used dots. So instead of writing the parameter in brackets, he wrote a dot. So the dot separates the parameter from the body of the lambda. And this is the body. So these are called lambda expressions or lambda terms. Grammar for terms. And then term has three variants. It's either a variable, it's an abstraction, which means that it's a lambda, which has a parameter and a body. The parameter is always a variable. Or it's an application of one term evaluated at another. And all functions in this sense have only one argument. So you would always evaluate only with one other thing. Does that make sense? So this is different from brackets notation only in that I've removed the brackets from x, from the variable. Is that good?
Yes, thank you.
Okay, so now let me show you what the rules of reasoning are. So the context gamma Basically, if you assume something, you give it a name, but that name is just a variable. The context consists of variable formula bindings, consist of bindings of variables. To formulas. So for example, the context gamma could be, let's say X is a proof of A and F is a proof of A implies B. But both of these are variables. So that's an important point. The bindings of variables, not of general terms, but of variables. And now the three rules of reasoning change in light of this. The first rule, which, so I'll write the old rules. The old rules were as follows. Gamma, comma, t proves t. This is the assumption rule. Then you have if using gamma and the assumption t, you prove w, then gamma proves t implies w. Implication introduction. And finally, if in gamma you can prove t implies w, and in gamma you can prove t, then in gamma you can prove w, implication elimination. Now we are going to modify these rules. So first off, our context gamma now has bindings of variables to formulas. Then if X is a proof of T, I can conclude T. And what should the proof of T be? If X proves T, then what proves T? This is not a deep question. What should I put here?
X.
Yeah. And in Prabhakar's notes, he says that since this operation is a looking up of your variable in your context. So if you have X and you want to know what it proves, you look it up in your context. Your context consists of variables. So this rule is now going to be renamed to the more dignified, as opposed to as, of rule called var for variable. So then we have this rule. Then the second rule is suppose that in context gamma, we have X as being a proof of T. And this, let's say, what letter do I want to use? I want to use, and let's say A. A is now a meta variable for some lambda calculus term. So this is a meta variable for some term. This doesn't necessarily have to be a variable. So if I can prove W with proof A, and x is some variable standing for proof of t, then what should the proof of t implies w look like? What proof term should I use here?
My guess is X implies A. Something.
What did you say?
X implies A.
Well, that's the proof terms are always going to be these lowercase t's, and lowercase t's are defined by this grammar, which doesn't have implications.
Okay. Then it will be applications.
Application of what onto what?
X onto A.
But x isn't necessarily a function. X is a variable, actually.
Okay.
Well, I mean, variables can stand for functions, but it's not a lambda expression. It's abstract. It's not an abstraction. What's the other thing that I can do? So if it's not application, then what's the third option? Okay, well, there's a third option. What's the third option? Anyone?
Abstraction?
Yes. So in other words, if we think of this as a proof of t implies w is a function that takes a proof of t and returns a proof of w. How does it do that? By substituting every occurrence of x in the body of A with the actual proof. So a proof of A implies w. This rule indicates that the BHK interpretation of a proof of t implies w is a function that takes a proof of t and returns a proof of w. And then our final rule, so this rule is implication introduction. And then our final rule is implication elimination. So suppose that in context gamma, we have a proof, let's call it f, of t implies w. So f is a meta variable standing for any term. And then in gamma also, we have a proof, let's say a of t. Then I should be able to conclude w. What should the proof term for w be? So if I have a function that takes a proof of A and returns a proof, that takes a proof of T and returns a proof of W, and I have a proof of T, namely A, then how do I get a proof of W?
Using the F on A.
You apply F to A. Yeah. So then you use a function by application to use f you evaluates. And here's the cool thing. So there are 3 rules for reasoning, right? There are 3 rules: variable, implication introduction, and implication elimination, right? And there are also 3 variants in the grammar of lambda calculus: variable, abstraction, and application. So Church's language of lambda calculus, the 3 rules precisely correspond to the 3 rules about reasoning for classical logic with for intuitionistic logic with implications. The rules have one-to-one correspondence with the variants of the grammar of lambda calculus. So in particular, if you look at the conclusion, if the conclusion involves a lambda term, then the only way that you could have a lambda term here is if you used implication introduction. This is an application. The only way you could have an application at the bottom is if you used implication elimination. And the only way that you can have a variable at the bottom, because remember, in the context, all of them are variables, is if you use the variable rule. So these are the rules for natural deduction. Now, let's think about this. Let's think about the proposition A implies B implies A. I want that line. That's not sequent line. That's just this. So how do I prove this? So a proof of an implication would be a function, right? Let's say I have a function that takes a proof of A. And then what does it return? It returns a function that takes a proof of B. And then how do I get a proof of A? So if X is, if you give this function a proof of A and you give this function a proof of B, how do you get a proof of A? So X is given a proof of A, Y is given a proof of B. How do I get a proof of A?
Just use X.
Yep.
Yeah.
So look at this proof term right here, lambda X, lambda Y, X. And let's look at this following sequence. So I claim that lambda X, lambda Y, X proves. I'll explain about how to remove brackets from things. There's a way to understand the bracketing so that this bracketing means that. So I claim that this is a proof of A implies B implies A. Now, remember that there are 3 variants in lambda calculus, and there are 3 rules. And the proof term at the bottom, depending on which of the variants it is, it has a unique rule corresponding to it. So here, the proof term is a lambda. So what rule does that necessarily correspond to?
The second one.
Yes. Now, let's look at what the rule looks like. Well, if I have lambda x a is a proof of T implies W, then I take x and I move it into my context as a variable. Remember, lambdas always have variables as their first thing. Their formal parameter is a variable. And then I can say that's that. So I would be able to conclude this if in a context in which x stands for a proof of A, I would have that the term lambda y dot x was a proof of B implies A. Okay, so look at the proof term here. What type of lambda expression is this? What type of term is it? Of the three variants?
Abstraction.
Yes, and so what rule does that correspond to?
Second one.
Yep.
Again.
So I moved that into my assumptions. Now, what type of rule is X? What variant is X of the three variants?
The context. Yeah.
No,
so
well, is X a variable, an abstraction, or an application?
that's the first thing. It's
It's a variable.
yeah, it's a variable.
And so the rule that I would try to use is the variable rule. Now, is this rule justified? Is X in my context with
Yes.
bound to A? Yes, it is. So the proof tree, I've constructed it automatically. So you can check at each stage, you build the next level automatically. Now, you can give a wrong proof term, but this is a process for checking whether your proof term is right. Why is this doing it? No, come on. Here we go. So let's try this. What is the proof term for A implies A? What should the proof term for A implies A be?
It's gonna be x dot x or lambda x dot x.
Lambda XX, which is the identity function.
Yeah.
So if you give me a proof of A, I can prove A. I just use the proof that you gave me, right?
Yeah.
So now remember when we were talking about Racket and we were talking about typing of functions in Rackets, contracts in Rackets. We considered the function define IDX X. And we said that it had contracts. This had contracts where we use type variables, A to A. So ID had type A to A. And this is the identity function. So in the BHK interpretation, terms then proofs and programs are identified. Or, well, we are, and then a term has a type. A proof, okay, let's say, well, a term corresponds to a logical formula. Well, a term proves a logical formula. A proof proves a logical statement. And a program has a type. So we think of terms, lambda terms, as proofs, and we think of proofs as programs. And we think of logical formulas, the syntactic objects, as the statements that we make in logic, and we think of those as types. And so the process of checking a proof is then type checking. Is the same as type checking a program. And this is what we'll cover in the second half of the class. So this is the topic of part 2. This is part 2 of the class. Okay, I'm slightly over time, and I guess I'll need to speak a bit because I need to introduce something at the start of next class before Prabhakar. But does anyone have any questions about this? So we'll go over this in greater detail. I was trying to rush to get to a certain point today, which I didn't quite get to. So I'll need to do a bit more tomorrow. Does this sound interesting?
It sounds interesting. It just was a lot to process today.
Right. Yeah, I agree. And I went over time and I tried to stuff as much in as possible. But don't worry, in the same way that we started doing proofs at the start of the course, and then we sort of did the same thing over and over again for a while, we are also going to now spend half of the course doing this. So we're going to stick with this also for a long time.
Okay.
So everyone should ensure that they come to tomorrow's lecture because we have a guest speaker, which is going to be good. Okay. Any other questions? And I'll send you the notes and a link to the homework and a link to the videos. And actually, Prabhakar's notes are very clear. They're really, really good sets of notes. So you'll enjoy those. Well, if that's all, then see you tomorrow.
Bye.
See ya.
Bye.
Thank you. Bye.
No worries.